We performed an experiment where we investigated a chemical equilibrium by noticing change in color. In the equilibrium system, iron 3 ions react with thiocyanate ions, and the product formed is a complex ion with a red color, which we can see. The reaction scheme is like this. This is a useful reaction since the left side of the reaction scheme is colorless and the other side is red. In this way, we can determine in which direction we have shifted the chemical equilibrium. First, we made the equilibrium mixture and later on performed some stresses on the equilibrium mixture. We can see the equilibrium mixture being made below. We always had one test tube with the original mixture so we could compare the color changed after a stress was performed. If we want to know the equilibrium expression, we have to look at the reaction scheme once again. It is crucial to notice that it is a homogeneous reaction, meaning that all the reactants and products are in the same state, in this case, aqueous solution. Furthermore, this is a reaction that happens in one step, and we can therefore use the general formula for the equilibrium expression, which is that if we have a reaction with the reactants A and B, and the products C and D, and they have the coefficients A, B, C, and D, then we can write the equilibrium expression like this. So we have the concentrations of the products to the power of their coefficients, and then we divide it with the concentration of the reactants to the power of their coefficients. The fraction on the right side of the equal sign is called Q, or the reaction quotient. So in our experiment, we have the equilibrium expression that the concentration of the iron thiocyanate divided with the concentration of the iron times the concentration of the thiocyanate is equal to K. And this is all to the power of 1, since their coefficients are all 1. The first stress we performed was adding 1 spatula of solid iron nitrate. So the stress was an increase in the concentration of iron 3 ions. On the macroscopic level, we saw a change to a darker red, which we can see here. This can be explained with Le Chatelier's principle. It states that if a factor that affects the equilibrium is changed, then the equilibrium will shift in the direction that reduces the change. So if we apply this theory, we add more iron 3 ions, which we know affect the equilibrium from our equilibrium expression, and this reaction will then shift in the direction that reduces the change, and it will therefore form more products in order to get less reactants. This is why we see the change in color to a darker red, since the product is red. We can also explain this mathematically if we take a look at the equilibrium expression once again. We know that K has to stay constant, so when we add more iron 3 ions, we divide with a greater number, thus giving us a lower value for Q, or the reaction quotient. For K to stay constant, we therefore also need a greater number in the numerator. The only way we can get this is if the reaction forms more of the product, and in order to do so, it has to use some of the reactions, leaving us with a lower number in the denominator, both for the concentration of iron 3 ions, but also for the thiocyanate. So we start with a greater amount of iron 3 ions, which will result in an increase of the product and a decrease of the reactants, giving us the same explanation as Le Chatelier's principle of why the color changed. The next stress we performed was in test tube 4, and here we added a few drops of silver nitrate solution. What we see on the macroscopic level is a lighter red and a white precipitate. In order to understand why it turns lighter red, we first have to understand why a white precipitate is formed. It is a precipitation reaction with the following reaction scheme. So what we see as the white precipitate is the insoluble salt silver thiocyanate. Potassium and nitrate are merely spectator ions. The reason why this affects the chemical equilibrium is because, as a consequence of the precipitation reaction, we have a lower concentration of thiocyanate ions, since some of them has been used. According to Le Chatelier's principle, we decrease a factor that affects the equilibrium, so the reaction will try to decrease the change. The only way to do this in this case is by increasing the number of reactants. This is why we see a lighter red, since the products are being used to form reactants. In these two stresses performed, it has been the reaction quotient Q that changed in the instant we performed the stress. In the next stresses, it is the equilibrium constants which changed at the very moment the stress is performed. This happened since the last stresses we performed was in test tube 5 and 6, where we increased the temperature in test tube 5 and decreased it in test tube 6. Since the equilibrium constant is dependent on the temperature, it is K which changes. It is important to note that both reaction rates increase when we heat the mixture, but one of them increased more drastically. The macroscopic observations are seen below. In test tube 5, we saw it change to a lighter red, and in test, which you can see here, and in test tube 6, it should turn to a darker red, which we can see slightly here. It's a little darker. We will explain the results in test tube 5 mathematically. We observed a lighter red, which means more reactants and less products. So we have less of the product, more of the reactants. This must mean a lower reaction quotient than before, since we now divide a smaller number in the numerator with a larger number in the denominator. Since it is not the reaction quotient, but the equilibrium constant that depends on the temperature, it means that when we heat the mixture, the numeric value of the equilibrium expression will decrease, and as a consequence, so will Q. The results we should have observed in test tube 6 we will instead explain with Le Chatelier's principle. Since temperature is a factor that affects the equilibrium, the reaction will try to decrease the change. So when we cool the mixture, the reaction will try to heat it. This can only be done by performing an exothermic reaction, meaning it releases energy. Since it should have been darker red, we now know that the reaction to the right is the exothermic reaction. This must also mean that the reaction to the left is endothermic. It makes sense since we in test tube 5 increased the temperature, which it will try to reduce by performing the endothermic reaction. And this will result in more reactants and less products, and therefore also a lighter red. The last thing I want to explain is why dilution with water shifts the equilibrium. The macroscopic observations are showed from above, like we see here, so we are sure to see through the same amount of molecules and are therefore also sure that the equilibrium has actually shifted. In order to understand this, we once again have to take a look at the equilibrium expression. Let's say we double the volume by adding water. As a consequence, all the concentrations will be halved, so we get the equilibrium expression like this. Now we can see that 1/2 cancel out with 1/2, but we still multiplies with it in the denominator. So we now get the expression like this. We now divide with 1/2 and get a number twice as big, since it is the same as multiplying with 2. However, K has not changed, so the reaction will form more reactants by using the products, resulting in a lighter red, so that Q still equals K. So we have less of the product and more of the reactants, since we need the same numeric value for Q.